There's a technical aspect to this talk, so we just wait for that to be ready, and then we'll get going.
Yeah, we're ready.
All right. All right, so welcome to the 8 o'clock talk by Dr. Ben Dorman. Always a pleasure when I get to introduce Ben. He is a good friend and colleague, of course, through the board. So Ben is the founding chair of the Friends of the Dominion Astrophysical Observatory since its inception in 2015. He received his Ph.D. on late stellar evolution from the University of Victoria. He then worked at the universities of Maryland and Virginia and at NASA Goddard Space Flight Centre on space observations of star populations and the integrated populations of galaxies. While working in the IT fields, he now describes himself as a recovering astronomer with a keen interest in the current developments. Ben, thank you so much for speaking to us this evening.
Yeah, I wasn't here last week, and you might have noticed the guy who did speak had similar interests. Anyway, I wanted to add that we are on the land of the Sinchothan-speaking peoples. Here of the Coast Salish Nation. I like to mention that we are trying to do our best to incorporate them in future plans for this organization, and hoping to get that going later this month. I kid myself that that's better than just giving an acknowledgement. Anyway, so what I'm going to do tonight is something almost impossible, which is to go a little bit beyond popular science explanations about stars and their lives and deaths. You hear about black holes and things going bang in the night and so on. I'm going to tell you a few of the details that usually get left out. Also, I'm going to try and relate it to things that we actually see with the Plaskett Telescope when we have you up in the dome, as we will do at 10 o'clock tonight, and actually image from the telescope. So you're going to see some images that were taken with the Plaskett. You're also going to see some images that were taken with somewhat larger telescopes a bit further away from Earth. So I'm going to tell you a bit, as this slide says, about what different stars do as they evolve and die. Actually, there's as much about stellar life that I could have called this the life of stars, but heck, you know, it seemed a little bit more sexy the other way around. So anyway, so I'm going to tell you how and why different stars do different things. And as I said, I'm going to show you what a few objects that you will be familiar with if you've ever done our dome sessions. And if you haven't, and you can stay until 10 o'clock tonight, then you'll see them tonight. So, first of all, there are more than two kinds of stars because there are lots of subdivisions, but there's real differences between low mass stars and high mass stars. And what's not, in a very simple way, we can ask, what is a star anyway? Well, it's something that has to shine, because if it didn't, it would collapse. The light that stars give out helps it not collapse against great mass that it has. So that's an important thing to bear in mind, because it changes exactly how stars behave. The bigger the star is, the more massive, I mean, then the more it has to shine, obviously, because there's more mass, and therefore it has to counteract more gravity. And the brighter it has to shine, the hotter it gets. All right? So that seems pretty straightforward, right? More mass, more gravity, more radiation needed. Okay, so now the hotter the star, the faster it goes through its fuel. That's because the nuclear reactions, which is all nuclear fusion, go much faster when the center is hotter. And So the most massive stars are about 100 times, give or take, the mass of the sun. So, okay, so it's 100 times the mass of the sun. How bright do they have to shine in order to avoid collapsing? Well, about 1 million times, it turns out. So what does that mean? It means that they don't last very long in comparison, because you're going to go through your fuel that much quicker if you have to shine 1 million times brighter. And throughout most of their existence, they're on what we call the main sequence. The main sequence is where they are fusing hydrogen to helium. And hydrogen to helium is the most efficient nuclear reaction there is. And that's because the difference between the mass of 4 hydrogen atoms and the mass of 1 helium atom is bigger. The difference is bigger than you get from any other nuclear reaction. So therefore, there's more energy to give out when they fuse together. So the massive stars run out after hydrogen, after as little as 1 million years, millions of years. You've all heard that the sun is probably, going to last about 12 billion years or so. So if you think about it, you can still make those plans to rearrange your living room before. I'll tell you that there are some other good reasons why that's a pretty meaningless statement, but we'll get there. So massive stars run out of hydrogen very quickly. They're 100 times the mass, they're 1 million times as bright, so they'll last 1,000 times less long, so they last for millions of years, not billions. So once they do, they quiescently, they just start burning fusing the helium to make carbon and oxygen. But the lower mass stars are those that are not massive enough to start helium without something drastic happening. We'll talk about the drastic bit in a minute. But the key thing is that is really the distinction between high mass stars and low mass stars. And they behave very differently as a result of this. The key thing is, well, we'll get there, I guess. First, let's talk about high mass stars a bit. They do switch on helium fusion quietly. That is, they don't do it with a bang. And that's because they're massive enough, they just get hot enough to be able to do that. The reactors that fuse helium to carbon need 100 million or 120 million degrees to work. And one of the reasons for this is because the nuclei are very energetic. But as you know, that carbon has an atomic number of 12, atomic mass of 12, helium has 4, so you need 3 of them to get together in order to this happen. And so they have to be very energetic to make that work. Once they can, however, make carbon and oxygen, they also, reactions are possible later on in their life when all the helium is used up to produce magnesium, silicon, and all the other heavy metals. It's a jolly good job they do, because otherwise we wouldn't exist. All of the elements that we're made of, apart from the hydrogen and the helium, and some boron, but there isn't too much boron around, all of the elements that we're made of are actually made in high mass stars in one way or another. So it's good. It's a good thing. And we'll take a look at some of the remnants later and show how it's very plausible to understand how the elements that they produce are spread out through the galaxy in a relatively short amount of time. Like, in a few hundreds of thousands or millions of years, a short time compared to the life of the galaxy, which means that, the galaxy has been around a lot longer than the Earth, and so there's been time for all this stuff to get distributed. Anyway, so the point is that each of the reactions that produces magnesium, silicon, aluminum, iron, all of these, making all of these elements actually produces less energy than the initial turning hydrogen to helium. And that's because, as I told you, the difference in mass between 4 hydrogen atoms and 1 helium atom is bigger than any other of these subsequent reactions. Eventually, when you get to iron, the fusion reactions actually use energy up instead of making it. And if you go back to my first statement, you will remember that stars have to shine in order to stop collapsing. So what happens when we get to iron? Well, they're not shining in the middle anymore. So, something drastic happens. It's not true that they're not doing anything, because you've still got all the stuff in the outer layers are still burning, but the main source in the middle goes out. So having just told you a little bit about all of the things that high mass and low mass stars do, I'd like to show this picture of a spiral galaxy. This is the well-known. This is called the Whirlpool Nebula, or it was originally. Now it's called the Whirlpool Galaxy. Now we know that nebulae are not galaxies are not nebulae. Yes, sir.
What's the drastic thing that happened?
I'll get to that.
Oh, okay.
I'm just pausing to show you what this actually, all of these different kinds of stars look like in nature. I've got two drastic things that happen. They're different levels of drasticness or drasticity, if that's a word. Yeah. Sorry? I'm getting there. So galaxies are no longer known as nebulae because back in the 18th century, they saw two kinds of objects in the sky, stars, and fuzzy stuff that weren't stars. And so they called anything that was fuzzy that didn't look like a star, they called it a nebula, which is a Latin word for cloud. So now, when we got bigger telescopes and figured a bit more out, we realized that there are way different kinds of fuzzy objects in the sky than clouds and stars. So we've also found many different kinds of galaxies which were no longer fuzzy objects, but through a telescope like the Hubble Space Telescope, they look rather like this. This is a perfect example of a face-on spiral galaxy, and this is one of the objects that we can usually image with the Plaskett Telescope when we have it. I think we can't do it tonight because I think it's set too early, but usually earlier in the summer we can do that. But the reason why I show you this is because you can see clearly different colors of different things here. And some of the different colors, all of them are due to stars. The blue spiral arms are due to high mass stars, and the yellow ones are low mass stars. And I'll go into this a little bit more in a minute, but the key idea is that these are very characteristic colors of galaxies. For those of you who think all these colors are fake, they aren't really. What astronomers do is they take many pictures through different colored filters. So they segregate out certain kinds of light to which different parts of the galaxy are sensitive, so that they can then register them all together and produce a color image, rather like your TV does, only with a lot more work. So when you actually see our Plaskett Telescope image this, you'll see a black and white version of this, but I'm going to show you some pictures taken with the Plaskett Telescope that have had equal amounts of image processing, and they look pretty spectacular. So as I was saying, yellow stars in the middle are old stars, and I'll show you exactly why we know this in a moment or two. Blue stars, these have recently formed. They're the young stars that burn out quickly. And the only reason why you don't get these blue stars in the middle is because the ones that were there have already burnt out, because as I told you, they last about 1,000th of the lifetime. So you also have this pink stuff, and that is actually hydrogen. Those are hydrogen gas clouds that have been illuminated by the stars, and those regions are about to form new stars. So this is the birth of stars bit. You will see in every spiral galaxy there are these pink knots, which are star-forming regions. And if you have ever seen, I don't have one here, but if you've ever seen pictures of the Orion complex with the Horsehead Nebula and the Orion's belt, you will see that it's got pink clouds in it, and these are exactly those. And the black stuff is a gas and dust that is not illuminated and obscures what's behind it. And I like to say that it's stuff that just does nothing and just gets in the way. Anyway, this particular galaxy has a companion which it's interacting with and pulling apart. But this is a fairly close galaxy. I think it's, if I remember correctly, it's 15 million light years away, and it's a spectacular object in the sky in a small telescope, and we can image this in 30 seconds with the Plaskett Telescope. And we will do that, but probably not till next July. All right, so now I'm going to tell you a little bit about where those red and blue colors come from. On the right-hand side, I have, I'm not going to go through this in detail because we can't have a short quiz at the end of the period. But the basic idea is that different stars of different masses, as we have heard, have different brightnesses. This is brightness and this is temperature. So as the star when it's formed is more massive, it starts life much hotter because, as you remember, it has to be hot. It has to shine more in order to stop collapsing. So the very massive stars are very hot in the center and very hot on the outside, up to 40,000 degrees. The sun is down here. And what these tracks off of this red line is called the main sequence. That is the sequence of stars that burn hydrogen in their middles, so the regular. And that is nearly 95% of the lifetime of most stars is on the main sequence. So what happens with time is that the stars slowly but surely get hotter, get brighter with time. And this is exactly why you shouldn't worry about the sun's end, because it's going to get too hot and too bright long before that. Probably give it 100 million years and we won't be here, but I think there are probably other reasons why we won't be here for that either. If you go back into paleontology, you will find that they know that the sun was 15% less bright in the Cambrian era. I believe that's the right figure. So if you go back 500 million years, the sun was noticeably less bright than it is now. So that's one of the things that affected climate back in the days before the dinosaurs. But this isn't quite as useful as the right-hand side diagram. So what you do, so if you say you've got a bunch of stars in a galaxy like that big spiral I just showed you, what you do is you expect that stars will form of different masses. So there'll be a few hundred solar mass stars. There'll be more and more, there are more and more low mass stars as you go down in the sequence. But there's a whole bunch of stars that are made at a given time, and they all start evolving. And as I told you, the top guys, the brightest ones, evolve fastest because they run out of fuel. And as I go down, they get slower, their evolution gets slower and slower. Well, what happens if you want to know, for a given population of stars that was born at a certain time, what it actually looks like on a diagram like this, luminosity against temperature? Well, you basically connect the dots between all of these tracks. You create models that evolve the stars up in time, and then you connect the dots at a particular time, and you get what's called an isochrone. Isochrone meaning equal time. This is where you get to see what the observations ought to look like. Because if I were to be able to look at a population of stars that were all formed at the same time and have the same material, I would expect it to look like an isochrone. Expect to look like a sequence of stars with the same composition, formed at the same time, but different masses. So that's what I get. So, an isochrone. And it so happens, but unfortunately, let me get to this in a moment here. So this is the first part of the story. This is what happens to stars that are burning hydrogen only. Eventually, they evolve off of the main, they go up the main sequence with time, and they eventually go through this turnoff, and then they go up the giant branch, which I'll talk about a bit more in a minute. But that isn't the whole story, because for the low mass stars, at some point they reach the top of the giant branch, and then we have to know what else happens after that. And so that's the next part of the story. Well, what happens is, for the low mass stars, they stop burning hydrogen purely burning hydrogen at the top of the giant branch, but also as they are getting there, they lose mass. And we know this. We've seen clouds of very massive stars with clouds outside, and I'll show you a few later. But the key thing is that all stars do this, but we don't know very much about the process. We still don't know around the process. And I did work on this 25 years ago, and we don't seem to know any more than we do now. But that's not because I haven't been working on it. These are problems that are inherently intractable, but every star seems to lose mass. And how do we know that? Well, if you actually look at, if you do models of stars that post this, I'm going to tell you about the drastic thing that happens, which is the helium flash. You get to a point where the star reaches the top of the giant branch, and then the core becomes dense enough and hot enough to start violent helium burning the helium. In the low mass stars, in the high mass stars, you remember, it happens quiescently. It just goes. But in the low mass stars, it doesn't. It waits for a flash to take place. And it also, for every star, it seems to happen all about the same mass. So after a short while after that, they settle down to have peaceful helium burning in the core and hydrogen still burning in the shell outside from their previous epoch. But depending on how much mass they lose, they end up on this sequence. And I've colored this sequence red to blue. And what I see is that depending on how much mass they got there, they will have a different temperature. And all of what I'm showing to you is observed. I'll show you some good observations in a minute. The stars that lost the most mass end up right over here, and they can be very hot. And all of this stuff here shows the later evolution, which we'll get into in a moment. But the key thing to realize is that once the star hits the top of the giant branch, all sorts of funny things happen afterwards. Now, here is some observations. This is another cluster we frequently observe nearly every night, and we will do so tonight on the Plaskett Telescope. These are called globular clusters. Now, if you remember, I said, wouldn't it be nice if we could look at a set of stars that was all formed at the same time with the same composition? That would make my theoretical models that I've made much easier to understand, because I wouldn't have all this confusion. Well, it just so happens that globular clusters, to a good approximation, are exactly those systems. There are about 150 to 200, I forget the exact number, circulating around our galaxy. They are old systems. They have between 70,000 and 2 million stars in them, and they look like this. That's why they're called globular clusters, because they're clusters. And if you were to take the stars in there, and I'd like to point out that we have software that can resolve every individual star in this really crowded field that you have in the middle of that. And the software like that is used the world over. It was invented right here at the Dominion Astrophysical Observatory, and so they came up with a computer program written in Fortran 77, for those who know what that is, called DAO Photometric Program. And so in other parts of the world, like Italy, there's something called RomaFOT, which is basically the same thing, only they're Italian version of it. Anyway, the basic thing is that if I were to take all of these stars and observe them to two filters, which allows me to measure their color and therefore temperature, and and you can see that some of them are bigger dots than others, they have different brightnesses, I would get a diagram like this. Now, if I allow you to go back a bit, that looks kind of familiar, right? On the right-hand side, on my isochrones, I've got a sequence that has a giant branch, and I also have a horizontal sequence going off of it, which shows that I actually do have stars, there's over there, that look like that, right? Oh, sorry. That's what happens when you press the wrong button. Okay, so here you go. So what I was just showing you theoretically is actually real. We actually do see systems like this, and we can measure these things quite precisely. The big snag is that it's very hard, it turns out, to measure what the actual light from giants are, and therefore to measure their temperature, but I think they've done better on that in the last 25 years than I remember. The basic idea, though, is that this is a really good reflection of what stars actually do, low-mass stars do actually in practice. If you look on the right-hand side, this is a crowded field from a globular cluster taken by Hubble Space Telescope. And just so that, to show you these things are real, I've got big red, bright stars in this, and I've got bright blue stars. So these are the big red ones up here, high luminosity, and these are the very blue ones, and they're not as bright. So this is from the Hubble Space Telescope. We have many, many cluster data from space, which shows us that this theory we have is pretty accurate. So what happens after all of that is, well, as you can imagine, sorry, I won't go there quite yet. If you imagine these guys, which are burning hydrogen and helium simultaneously, one in the core and one in their shell, they eventually run out of helium in the core, and so then they tend to ascend and become like giants, just like they did before in the hydrogen burning stage. And eventually, just like I said that they were just shedding mass during going up the giant branch, they do it again. It's called the asymptotic giant branch, and the reason why is because it sort of asymptotically tends to the other one. So if you remember your math and what an asymptote is. But anyway, you can see this sequence on the left tending back towards the sequence on the right. Asymptotic giant branch. Asymptotic giants actually do all sorts of complicated things, but the key thing is the evolution gets really fast, and eventually they expel their envelopes very quickly, and we end up with what is called a planetary nebula. So this is near the end of the life of a low-mass star. This picture is M57, which we always also observe with the Plaskett Telescope. It's usually the first thing we look at, because right up high in the sky, near the star Vega in the constellation of the Lyre, it's about 11th magnitude, which means it's about 100 times fainter than you see with the naked eye, but with a 72-inch telescope, no problem. So the basic idea is this is the best picture we've ever seen of this, and it was released on Tuesday from the James Webb Space Telescope. And you will see this if you go to our observing sessions. It's quite the thing. So the other cool thing about this is the outer layers. You remember I said that hydrogen shines out red. Well, here's hydrogen layers, and oxygen, I didn't say, but is true, shines out blue. So this is exactly what you would expect from a spherical object that is expanded with hydrogen on the outside and oxygen and carbon in the inside. And right in the middle, I have a white star, which is the core of a white dwarf. Now, a white dwarf star is essentially the core, the helium-exhausted core, the carbon-oxygen core of that star. Now, the planetary nebula is very bright, and the gas expands. This is several light years across by now, and all our lower mass stars do this. Of course, the more envelope they have, the different their nebula. The other thing is I've got an outtext at the end, all the things I don't get a chance to say because I haven't got time, and I'm speaking fast enough anyway. So one of the things about planetary nebulae is that they are heavily influenced by magnetic fields, and so you see all sorts of twists and turns in the sides of this envelope outside, and we'll show you the Dumbbell Nebula from the Plaskett, which also is a planetary, and it shows all of the gas coming out through magnetic field lines. Anyway, some more massives do this, but there's a limit to how big a white dwarf can be, and it's about 1.44 solar masses. A famous Indian physicist called I won't pronounce his first name, Chandrasekhar, who has the Chandra X-ray Observatory named after him. He won a Nobel Prize for his work on black holes. He discovered the limit that white dwarfs cannot exceed. It's about 1.44 solar masses, but the cores of our very low mass stars are only about 6/10. So some of the stars in between the very low mass guys and more massive stars, shall we say, do this too. Anyway, so this is the last so the last chapter is a white dwarf. The white dwarf is inert, it just cools. It takes a long time to do it, and we actually use white dwarf cooling curves to things like date objects, because seeing how far down the curve the white dwarfs are tells us something about how old the object we're looking at is. Okay, so now fireworks time. So we're now going to talk a bit about the high mass stars, and this is the stars that are too massive can't just do this white dwarf thing. Eventually, the core cannot be supported by nuclear fusion because all the reactions run out, as I was saying. And since they can't create the necessary energy to keep gravity away, they collapse and explode. Now, the remnant is going to be a neutron star, a black hole, or absolutely nothing, because the stars can actually completely blow themselves to bits. And this is stuff you may have heard before. This is why I'm not doing it as much detail as the other stuff. Supernovae, however, are either seen without hydrogen or with hydrogen, and they're classified as, I got that, I forgot. Type 1 supernovae do not present with hydrogen envelopes, and type 2 do. This is the most recent supernova in our galactic system. It happened in the Large Magellanic Cloud in 1987 in January. It was discovered by Canadian astronomer Ian Shelton, and that's not why it's called 1987A. It's done because they label supernova in any year A, B, C, D, E, F, G, depending on in serial order. So that joke works better in Ontario. So these are pictures from the Hubble Space Telescope. This happened in 1987, and 1994, 95, you see how this develops, and eventually it seems that this ring there existed outside the star before it exploded, because it's already well separated from the center. And eventually, by the time you get to 2003, which is 16 years later, material hits the ring and starts lighting it up. So we see, it's quite incredible that we see objects in the sky that we see evolve basically as we look. Now, about supernova detection, well, I said that was one supernova that was in a system near our galaxy, but if you look at the historical evidence, we've only seen 1, 2, 3, 4, 5, that's 1604, not bad line rat. Yeah, so we've only seen about 6 of these in the galaxy. However, if we look at, there are lots of galaxies out there, right? So if we look at other galaxies, we do see a lot of supernovae. There's a guy who saw 80 who lives in Prince George. Actually, he was on CBC a couple of years ago. He discovered 80 supernovae in distant galaxies in 1 year. So we do this with the Plaskett Telescope, and if you look at some of these images carefully, you see galaxies with spots on the outside, which are supernovae in distant galaxies. And that's one of the main things the Plaskett Telescope is used for scientifically, is to verify supernovae in distant galaxies. So I just want to show you this composite slide sent to me by the observer of all of these galaxies with bright spots that were eventually confirmed to be galaxies, to be supernovae. And this, what they do here is, so just to make sure that this is not just a smudge on the lens of some observer in Japan or whatever, they actually use the Plaskett Telescope to confirm that it has the right behavior. So here's 2 instances. The one on the left is a cheat. It's actually not a supernova, but it's a nova. But supernovae do the same things. As time goes on, they get fainter, and lines in them get less pronounced. Now, the lines in supernovae, they are very violent, and they actually create chemical elements that are more massive than iron, and so they create radioactive isotopes, actually. So a lot of that is due to radioactivity. On the right-hand side, I have a fit between a spectrum taken at the Plaskett Telescope with a library composite of that kind of supernova. So I'm saying that, so this is a confirmation because it's saying that the supernova that we observed is compatible with other supernova we have previously observed. So the black is the spectrum and the red is the fit. And this galaxy is 112 million light years away. So this is how far we can see with our telescope up here. So particularly in the winter when lights are long and you can focus on the same thing for a long time, you can see really deep with that telescope. And also our detectors are 10,000 times more sensitive than they were back in 1918. That's one of the things that gets changed. What was I going to show you next? So here's another example of a supernova. Remember the asterisk? Do you remember the asterisk? So I actually was queuing this up so that someone would ask me about it, but I'm going to tell you, not all supernovae are due to the core collapse of a massive star. Some are produced by a mass falling onto a white dwarf. And when the white dwarf hits that limit that Dr. Chandrasekhar defined, then the thing has to collapse, and then the rest, you know, right? It's no longer able to be stable, and it goes boom. And there's an artist, I would like to say that's JWST data, but that's an artist impression of what might happen. This little white dwarf is pulling matter off a star that is orbiting around it, and eventually it gets too massive and boom. You get what's called a type 1a supernova, and they have a distinct spectra from the ones that collapse. But as I said, type 1 supernovae show no hydrogen in the data. So you expect a white dwarf not to have hydrogen because it's basically carbon and oxygen only. Okay, plus heavier elements. This particular object that has been observed is twice as far as the one I just mentioned. It's like 250 million light years away. So seeing quite far tonight. So just by coincidence, here is another object we observe nearly every night. We are up here. This is called the Pinwheel Galaxy, M101. I know people have heard of Messier. He wasn't the hockey player, but he was a comet hunter back in the 18th century, and he created this catalog for people who, remember this were the days when there were either stars or nebula. He was a comet hunter, and he wanted his chums who were comet hunters to know that these fuzzy objects weren't comets. So he created this catalog of 110 objects, which are not comets. They happen to be some of the brightest and most interesting objects in the sky, but to him they weren't comets, so that was the important thing. Anyway, he created, this is a picture of this galaxy taken sometime in the last 10 years, I don't exactly know where, but you can see this is the same galaxy, and there's a bright star there, which isn't in the other one. And the people who observed this were members of the Royal Astronomical Society of Canada, Victoria Centre, who happened to have the Plaskett Telescope the very night that this supernova was discovered. And so they happened to get an image of it, and this data, reduced from the Plaskett Telescope, full color image, created from the telescope data, had a beautiful picture of the supernova. So, and that was actually used in scientific work subsequently. So while we're talking about supernovae remnants, here's one from the Plaskett, and here's the equivalent of the Hubble Telescope picture. Now, the Crab Nebula, you know where the name comes from? There was this guy called the Earl of Ross. He was an Irish lord with a lot of money and a lot of land, and he built himself a big telescope. And he lived in the 1850s. He did this in the 1850s, so he had to, there were no photographs back there, so he would sit at his eyepiece and sketch. And he thought this thing looked like a crab. So he called it the Crab Nebula, and the name is stuck. He also named the Whirlpool Nebula, but he was a little bit more accurate with that. Anyway, so The Crab Nebula imaged with the Plaskett, imaged with the Hubble Space Telescope. This is the remnant of the star that exploded in 1054, was observed nearly everywhere else except Europe. It cast shadows during the day when it was brightest, and it has produced this cloud in the meantime. Now, this is the most amazing object because they discovered a neutron star in it, a pulsar that is spinning every 33 milliseconds. And those asterisks are to me to remind you that it's not the record. There are stars that spin faster than that. It's about like a blender. You can imagine this thing weighs as much as the sun. It's 10, 15 kilometers in diameter, and it spins 33 times a second. And we know this because we've actually seen it. We can put a stroboscope on this thing and observe it. And if you look carefully on YouTube, on the web, you will find the Chandra, named after Chandra. Here's the satellite that has observed this has actually seen swishing of the light around this nebula caused by the neutron star at that rate. So, you know, astronomy, although it sounds like everything is so far away, you can directly observe things happening in the sky with the instruments that we now have. Okay, so quickly back to 1987A here. It just so happens that I think Friday, James Webb Telescope released this picture of it. So you remember we had those rings with the beads around it. So this was what Hubble saw, and this is now what James Webb has seen in the infrared. So there is the ring that you have seen with the beads on it, where the gas from the exploding star has slammed into that and lit them up, but you also see there's plenty of material outside. So there's an evolutionary history around this supernova, which we really don't know anything about, and we are just discovering. One of the real problems with supernova detection is, not detection, research is we never, ever know what the progenitor star looked like just before it exploded, because particularly when it's in a distant galaxy, of course, because you can't see it anyway, too far away. But even a close object, relatively close object like 1987A, you just cannot see what the star was before, because you don't know which one it was. And in particular, and if you did know what it was, the chance of you actually having looked at it just before it went off are at 0, because there are quite a few stars out there, right? And when I look at that one. Right, so anyway, but it does tell you that there is interesting structure around an exploding star, and that it was clearly in some serious trouble even before it actually exploded. And this is the inner ejector. This is the stuff that has just come out of the center sometime in the last 16 years, because we know actually when the thing went off, thanks to Ian Shelton of the University of Toronto. Okay, so finally, here's some conclusions, and the outdex, that's all the stuff I left out. And I probably left out stuff out of this list too, so don't worry about that. Deaths of the stars produce planetary nebulae, they produce supernova remnants, and those supernova remnants contain neutron stars and black holes, generally speaking. Sometimes they contain nothing, or at least nothing we've seen so far. And while the low mass stars end up as planetary nebulae, which have big gas clouds which disperse and white dwarfs that slowly fade away. High mass stars go through the supernova experience. Quite different. The supernova, if I didn't say this before, you've seen that in distant galaxies, it's the brightest spot in the galaxy. So imagine it's outshining all the other stars in there, all 100,000 million of them. Pretty dramatic. That's why it's drastic, by the way, just in case you were worried. So things I didn't get time for. Well, the neutron stars were, there's a paper called On Massive Neutron Cores, which was written by Oppenheimer and Volkov in 1939, just before he got called away to be the star in a movie. That's what he was known for. I was actually doing theoretical astrophysics before that. Type 1 supernova creating white dwarfs. I did mention this a bit. One particular supernova occurs when the white dwarfs accrete matter, and the nova, the A nova, which is actually the spectrum I showed you decay, it's the same process, only it's not violent enough to blow the star to bits and can happen more than once. Supernovae tend to happen only once to the same star for reasons you can probably imagine. I didn't get to show you that neutron star video from the Crab Nebula, but I recommend that you look it up if you find this interesting, because it's pretty amazing. It's only 30 seconds long, so you can do it during the commercials. There are some even weirder stars that are neutron stars, called magnetars, that are strongly magnetic. They have magnetic fields that I think are 100 million times stronger than the sun's magnetic field, and that changes everything about the way the light comes out. So it's in the outdecks, other things to follow. And I didn't talk about black holes because everyone else does. Thank you very much. Whoa. Any questions?
This is probably a basic.
I'm going to show you the mic.
Oh my gosh. Okay.
Here on stream.
This is probably a really basic question that people know the answer to, but I was wondering, when you talk about how bright stars are, when you're studying that, do you need to account for distance, or because they're not moving through an atmosphere, is the brightness not impeded?
No, that's a good question. So we do need to account for distance, of course, but we also measure the quality of the light from a star and see that two stars at different distances have the same quality of light. You do that with a spectrograph, and then you can see that they're actually the same kind of star but at different distances. One of the key things that astronomers do is determine the distance particularly to the globular clusters, and ultimately an even bigger question is, because we can calibrate using different kinds of stars that do the same things, that's how we ultimately can construct the distance scale of the universe. So yes, it's an important question.
Okay, there's two questions. One was regarding kind of like, it was a few slides ago regarding kind of like the energy the stars hold on to. Could that be kind of be similar to like deep sea free water divers and how they hold onto their breath? Could that be one way that could be looked at? It's like
I'm not sure I understand the question.
Free divers, how they hold on to their oxygen when they go to stored depths, and when they come up it expands. Could that be used towards?
Right, that is actually the operation of physical law. That's how pressures, temperature, and density relates. Yeah, that is one of the physical laws that you of the.
That be sort of how the stars the way how it develops their energy and expand it.
Not exactly. Because your diver isn't really influenced by, it doesn't have gravity differentials and all those kind of things. I'm not quite sure I answered that correctly, but
I have.
okay.
It was answered. Thank you.
Can I ask a question?
Yeah, sure.
Wow. Do you want to clap? Sorry, could you explain how first stars was created after Big Bang?
How first stars created after the Big Bang? Well, first of all, at a certain point, there was no elements. So you had to wait for things like hydrogen and helium to form. Then systems that contain gas collapsed into galaxies. If you look at, one of the most amazing things is that if you look at the data about the cosmic microwave background, which is where we know about the Big Bang from, it's a perfect fit to laws of physics of black body of radiation, apart from tiny little perturbations, small changes, which are of the order of 1 in 10,000, and those we think those small perturbations eventually are the ones that where mass accumulated into galaxy clusters, and then galaxies, and then clouds within galaxies that eventually produce stars. So there's a whole bunch of things that had to happen before you got there.
What was that point you say?
What?
What was the material at that point?
So these were energy fluctuations. So energy and matter being.
How they created from hydrogen, as the science says that after Big Bang for 200 million years, we didn't have anything except hydrogen.
And possibly some helium.
Some helium.
Yes.
And is it possible for them just because of some small unbalancing to create this amount of this big gravity to create first stars? Is it enough?
I actually can't really. I really don't know the answer to that question. As I understand it, the stars formed after the galaxies were able to get together. And that's the best answer I can give you. The stars didn't form directly out of the Big Bang. But there is controversy about were stars able to form with no higher elements of hydrogen and helium? That's a big question. Were you asking something?
Why are there big black holes in the center of every galaxy?
So the black holes in the center of galaxies are a slightly different phenomenon, because these black holes will be formed from one individual star, but the centers of the galaxies seem to get very dense and they attract matter inwards like stars. We can actually see stars orbit really fast around the center of our galaxy and slowly getting pulled in. So that's why we know that there's probably a black hole there, because nothing else could make these stars move so fast. But we think that they are probably the result of many stars ultimately falling in to that point. So, but actually, the truth is no one actually knows the answer to your question. It's a big question. We think we see black holes in very old systems, so they may have formed very early on. But it's an open question. It's a good question. I have to stop because I need a break, and I'm on again in 2 minutes.
Okay.
All right.
Hi, everyone. Welcome to What's Up in the Sky for September 2nd, 2023. Be sure to check out our gift shop in person or online. And we're grateful for your memberships and donations, which help keep our educational programs running. And in keeping with that, notice that we have summer daytime hours, so stop by and say hi. And we'll be doing dome tours and planetarium shows throughout the day. So the summer daytime hours continue to September 29th. And are as follows. They're Tuesday to Friday inclusive from 10 a.m. to 3 p.m. And note that there is an admission charge, and funding through grants has dropped this year. And so we do need to raise money. And so that's why we're charging for admission. And so for seniors, that's age 65 and over, is $12. Adults age 18 to 64 inclusive is $15. Students age 18 to 25 with valid student ID is $8, and that's the same for youth age 7 to 17, also $8. And children 6 and under are free, and members of the Wasonic community are also free, as the observatory resides on their traditional territory. And note that the name of the mountain in their language is Witixis. A little bit about sunset, twilight, and sunrise times. Sunset is now before 8 p.m. and was at 7:53 p.m. tonight. Sunrise was at 6:32 a.m., 10 minutes later than last week. And the sun was at its highest point at 1:13 p.m. at 49 degrees above the southern horizon. And on the equinox in a few weeks, it'll be at 42 degrees above the horizon. So why am I mentioning the altitude of the sun above the horizon? Well, as the sun becomes lower in the sky, and it's now nearly 20 degrees lower when it's at local noon, the concern about sunburns due to ultraviolet radiation also lessens. Though if you plan to be outside for an extended period and you happen to be sensitive, consider protecting yourself. And I'm also mentioning this because people tend to put on sunscreen when it's warm, but it's really the amount of ultraviolet radiation making its way through the Earth's atmosphere that and how long you're outside that determines whether you're going to get a burn or not. So, for example, in late June, it was probably cooler than it was today, but the chance of actually getting a burn was actually much higher because the sun was at its highest in the sky. And I'm just going to show a chart here from victoriaweather.ca, and this is from a field station at Oakland's Elementary School, which is just south of where I am and also just south of the Hillside Shopping Center. And you can see this curve over here, which shows that the sun, even when it was at its highest in the sky, only reached about a 2 on the UV index, and it's colored green because it was relatively safe to be out at that time. But if you were to look at this at around the time of the summer solstice, this would have been much higher, probably 8 or even higher, and colored red, because there would have been much higher risk to having a sunburn. And also the length of the day was also longer as well. Okay, so I'm just going to stop sharing there for a second, and I'm going to flip over to one of my favorite websites, as many of you know. It's called spaceweather.com. And just bear with me for 2 seconds while I make my way over there. Okay, and you can see this beautiful image here made from Alaska last night, and it shows the northern lights overhead. And I saw a display almost exactly like this almost a month ago, and from a campsite in Jasper. And you could see the patterns that you see here moving around in real time above you, and it was just a most extraordinary sight. That was the best display I'd ever seen. We're actually coming into solar max now, and so this will become more common. So please keep your eyes peeled on this website. And in fact, I was just checking it, and I could see that in fact there's a geomagnetic storm going on. If you look over on the left-hand side by this thing that says current auroral oval, down below it says planetary K index, and it says that it's currently a 5, and this might actually get even become an even bigger storm as the evening goes on. And if so, there's a good chance that the auroral oval, which is where you can see the aurora, that will cover up Vancouver Island. So you might actually have a good chance of seeing the northern lights tonight. So make sure you're away from city lights and let your eyes adapt to the darkness for at least 20 minutes. So don't be looking at your phone or anything like that, or turn a light on by accident. And look towards the northeast. That's probably your best chance of seeing the northern lights. That's kind of towards Vancouver. Okay, so I'm going to stop sharing there for the moment. All right, so there were 13 hours and 20 minutes of daylight today, and that's 24 minutes less than last week. So already almost half an hour less daylight than last week. And astronomical twilight ends at 9:46 p.m. and begins at 4:37 a.m. So the moon phase is past full and is about 80% full right now in what's called the waning gibbous phase. And as noted last week, the fire smoke and moonlight caused the night sky to appear quite bright at night, as we had moonlight from above shining down on the fire smoke, and we had light pollution from below shining up at it, and so we also had the dimming effect of the fire smoke itself blocking starlight coming in. And so all of this combined to mean that the sky looked quite bright, and we couldn't see the stars very well at all. You could only see a few of the brighter ones and maybe the planets and so on, and the moon. And so thankfully the fire smoke is gone from for the moment from the Victoria skies. And you've also probably heard that there's a super blue moon this week on this past week on August 31st. And the blue part means that it was the second full moon in a month, and the super part means that it was relatively close in its orbit. But of course, due to the fire smoke, it doesn't look blue at all, because the fire smoke tends to make things look red, but it wouldn't have looked blue anyways. It's just a historical name given to this seeing it, the moon, full moon twice in the month. So the attention given to the whole supermoon phenomena is a fairly recent thing, and it seems to be just this persistent clickbait thing on the internet. And but most people will not actually see a difference in size between a full moon close to us in its orbit, and a full moon far away from us in its orbit. So what you can notice is when the full moon is near the horizon, it tends to look bigger than when it's high up in the nighttime sky, such as in December. And that's due to something called the moon illusion. But if you were to actually measure the angular size, you will not actually see any difference in angular size. Okay, so we keep talking about that because it keeps coming up. So a little bit more about the moon phases. The moon will be at last quarter on September 6th. New moon will be on September 15th. And of course, that period is a great time for looking for fainter objects in the nighttime sky. First quarter will be on September 22nd. And the harvest moon, the full moon, will be on September 29th. Okay. And I'm going to share my screen again here, and hopefully we can get another image up. And just bear with me. And okay. And as for the sun and moon, there will be an annular solar eclipse on October 14th that follows a similar path to the total eclipse of 2017, in that the maximum phase cuts through Oregon. So, but unlike the 2017 eclipse, you must keep your eyes protected at all times to observe this one, even if you're right in that zone of maximum eclipse. An annular eclipse occurs when the apparent diameter of the moon is less than the apparent diameter of the sun. And note that both the sun and moon have changed in terms of their relative distance from us throughout the months and throughout the year. Nevertheless, Oregon should be a good location. My wife and I won't be going there, but we wish clear skies to everybody who is. Okay, so I'm going to stop sharing that and hopefully share Stellarium here. And the time on the clock over here, you notice it says date and time. There's the date, and the time is over on the right-hand side here, and it's in 24-hour clock. So it's currently set for about 10:25 in the evening. So Saturn, which you can see down here by the southern horizon, rises at 7:40 p.m. and it's becoming well placed in dark evening skies. And it's always a great target for small telescopes. You pretty much always see the rings to some degree, even if it's just a bit of a bump on the planet. And Jupiter comes up just after 10. You can see it over here. And you can see its moons even in binoculars, okay? And if we just advance the date just a couple of days here, you can see the moon is going to be passing Jupiter September 3rd and 4th. So if you're having trouble identifying Jupiter in the nighttime sky, you can use the moon as a guide. Okay, and I'm just going to move the time now to early morning. And I hear that there are some people who actually get up at this time of day. I don't, but nevertheless, let's have a look over towards the east. And we can see that Venus is now visible in the morning sky, rising at 4:23 a.m. And Sirius is actually visible to its right. If you actually just advance the time a little bit here, you should see Sirius coming up. There it is, okay? And when we see Sirius coming up in the morning sky, that means we're in the dog days of summer, as we said in previous weeks. All right. And just a note here before we get into a few things. Note that with sunset becoming earlier each night, we won't have to worry about losing our view of the summer constellations just after sunset for several months. So you'll be able to see many of your favorite summer constellations for the next few months, weather permitting. And now that we have relatively smoke-free skies again, I'd like to see if we can identify something a little bit different here in the sky. And I'm just going to move it back into the evening sky for tonight. And I'm going to advance the date here just a little bit and maybe look overhead. And I'm going to get the time out of the way here. And we're going to bring up some constellations. Okay, I'm going to see if I can get this set right here. And you can see Cygnus is here, and Lyra's over here, and Aquila's here. Remember, that's the summer triangle. And we also have a fairly it's called an asterism, as it's not a constellation. It's made up of bright stars and 3 constellations, as we were saying in previous weeks. But we see a constellation over here, the Cepheus, the Queen. And what I'd like to do is to draw your attention to a star there that is not particularly bright. And I'm hoping that you can see it, that you're in conditions that will allow you to see it. It's this one right here. It really doesn't look like much at all, does it? But it's actually one of the most important stars in the sky, because it was because of work done over 100 years ago. And so let's just talk a little bit about that. So this star is actually called Delta Cepheus, and it's a pulsating star that varies in brightness between magnitude 3.48 and 4.27. Remember, the smaller number means that that's brighter when it's at 3.48 than when it's at 4.27. And it was first identified as varying in brightness way back in 1784 by an English amateur astronomer by the name of John Goodrick. Hopefully I'm pronouncing his name correctly. And it varies in brightness every 5.4 days. So it goes through the full cycle in brightness every 5.4 days. And it actually rises in brightness faster than it fades. Okay, so this star, a little bit more trivia about it. It's about 800 light years away. And there's actually a brighter and more famous star nearby to it in the sky. It's right over here, and that's the star Polaris, the pole star. Okay, and it's actually called a Cepheid variable, named for this Delta Cephei that we were just talking about. And it actually varies in brightness between 1.86 and 2.13. So remember earlier we said that a smaller number means brighter. So it's a brighter star in our sky. And it's about, the reason it's brighter for the most part is because it's about half the distance of Delta Cepheus. It's about 445 light years away. And the first star of this type, however, was first noticed just a few weeks before Goodrich's discovery. And see if I can target it over here. And it's Eta Aquilae. And hopefully, yes, I think I've got it. It's right over here. So it's near Altair in the sky. So there's a challenge for you to find all 3 in the sky. So why are these stars so important? So the Delta Cepheus was very well studied by an American astronomer, professional astronomer, and she discovered a relationship between how long it takes to change in brightness and its intrinsic brightness, its wattage, if you like, how much light it actually puts out. And that discovery now bears her name. It's called Leavitt's Law, in honor of her and her name is Henrietta Swan Leavitt. And this law was crucial to determining the existence of other galaxies by Edwin Hubble in 1924. So it's 99 years ago. We're coming up to the 100th anniversary of that. And he discovered a Cepheid variable in the Andromeda Galaxy. And well, the Andromeda Galaxy is visible right over here. It's a fuzzy little patch in the sky. And I always find it by looking for these 4 stars in Pegasus. Looks like a big box in the sky. And then find 1, 2 stars over, then 1, 2 stars up, and then you should see that that fuzzy patch in the sky. And so, using a telescope in California, he identified a Cepheid variable, measured how long it took to go through its cycle in brightness, and realized that to be as dim as it appeared in his photographs, it had to be very, very far away. And so this settled the debate about what some of these fuzzy patches in the sky were, and proved that there are other Milky Ways, other galaxies out there. And Hubble gave Leavitt credit for her important discovery, which all of that was based on. And he said that had she been alive, she would have won the Nobel Prize for for this discovering this crucial tool for finding distances in the universe. And really, this is one of the primary projects of the Hubble Space Telescope in the 1990s, was to use Cepheid variables to find distances to much further galaxies. So, so that's about it for this week, and I'd like to thank everybody for listening, and as always, please keep looking up.